Is Dieter Kranzmu from LRZ, who's going to talk to us about general purpose supercomputing on SuperMUC, the large machine at LRZ.
So, good morning everybody, and thank you for the nice invitation. We just found out that Munich is very close to London, so it took me a little bit more than 2 hours, just door by door or something like. Transportation is really interesting. Now, I should also give you a little warning. We're changing the topic here. I'm just a little computer scientist, and the application talk that we just heard is a little bit different from what I'm going to tell you. My role is more like enabling people like you doing the research, and I want to show you what we have been doing with respect to supercomputing on SuperMUC, which is the name of our machine, as Peter mentioned. And the special characteristic of SuperMUC is it's a general purpose machine, and that has a reason. So let me first give you a little bit of an overview of the Leibniz Supercomputing Center. And what you see here is basically these 5 buildings. Now there's people working here, of course, and we have about 250 staff members, including student personnel and all those people taking care of the 24-hour shift. Of course, we're not only doing supercomputing, we're doing other stuff like the Munich Scientific Network, which has about, just to give you one number, 4,600 kilometers of cables. We're doing a visualization center. We're doing all those kinds of services that scientists need for their daily work. And we do that for about 100,000 students in the area, about 30,000 employees, including about 8,500 scientists. So in our first role, we are the computer center for the Munich universities, and they get kind of basic support for their daily work. When you're a scientist, you sit at your desk, you want your email to work, you want to have access to a big printing machine, these kinds of things. The second level is that whenever things get bigger, you need to concentrate in order to put more stuff together and to use that efficiently. We're doing that on a regional level for the state of Bavaria, and we are running a number of clusters, which are comparable to other clusters which you have at your university, which have different characteristics depending on whatever the respective scientist needs. And then we are one of the 3 national supercomputing centers. Together they call the GCS, the Gauss Center for Supercomputing, and we're providing the highest level of performance, of computing performance, to the German scientists. So the German government, together with the 3 states, sponsors our machines, and we are trying to get a new machine every year at one of the 3 centers, having a nice cycle, making sure that all the application requests are fulfilled. And part of that is also what we say is the European Supercomputing Center, means that some share of this national event, of this national strategy, is also to collaborate with people on the European level and to provide some of these cycles. Now the machine was already mentioned. Here is a little picture. That is SuperMUC, and SuperMUC is actually 2 machines. We have one machine which is in the background here. So the entire room has about 1,200 square meters, and I can also show you where it is. It is actually the top level room of that building here. And inside there we have this room with 1,200 square meters, and SuperMUC phase 1 is about half of the room. SuperMUC phase 1 was installed in 2012, has about 150,000 cores, and together it provides a peak performance of about 3.2 petaflops. Whatever that means, let's have that standing here. Now, interesting enough, that was built in 2012. This is the upgrade. This is phase 2 that came in 2015. As I said, 3 years later. And interestingly enough, here we have only 2 rows of cabinets. We need about a quarter of the space, and we need only a third of the electricity of phase 1, and we get the same performance, which is the typical thing that everybody knows, Moore's law. If you wait long enough, the machines get small enough. Now the point here is, this is the big machine in the sense where you can apply for cycles. Peter mentioned it, you don't have to pay anything. You pay with your good name. That means you propose, you put in a proposal, you kind of qualify your research, and as long as you're doing good research, you're getting on this machine. Actually, there's a second factor. The second factor is you need to be big enough. So the machine is really intended for scientific effort on computing, which is big and cannot be done on any of the departmental or university clusters. So we are fulfilling a niche on the one end of the spectrum. We are trying to provide computing power that goes beyond what you have on your desk. And then, of course, you need to fill in with these other things. So when you mention cloud, for instance, it is, of course, important that there is a cloud somewhere for those who need the cloud. But once we want to get to this machine, to this level, you would need to get access to that machine. And the typical allocation on the machine, just to give you an idea, is somewhere between 15 million CPU hours and 80 million. And I think the average is more 80 million like, yeah? So we are talking about 80 million CPU hours on one of these machines for one of the allocations per year. That's what these people have to spend. Now the question is, why are we doing this? This is not for production, obviously. This is for frontline research. But the idea is, and Peter, you mentioned, is it just for academic purpose, yeah? And luckily, yesterday he explained to me what academic purpose means with soccer and football, yeah? Now the question is, this for academic purpose? Well, actually, if you take a little think, and I'm doing shameless product placement here, yeah? If you take out your smartphone, and actually if you could go back in time 20 years, 25 years, 30 years, if you go back 25 years, this would have been one of the 100 most powerful machines on the planet. Now, if you think of that, it is of academic purpose today, but if we think 25 years in the future, maybe we have that computing power somewhere here with the medical practitioner in the hospital going through and then doing the same simulations that we're doing. And that is, I think, the idea, and that's why we are doing this and providing. Now, SuperMUC has, as I said, one important qualification. It is general purpose. The idea that we are always following is that we have a wide variety of applications. Actually, there are 200 different application domains running on SuperMUC. This is just an example. So we have everything from computational fluid dynamics, astrophysics, biophysics, you name it. And that has to do with the characteristic of SuperMUC. SuperMUC is a general purpose machine. It uses the same processor as my laptop. The difference is it has 230,000 in total. And you can use all of these 230,000 together in order for you to do your applications. Now, strange enough, SuperMUC, when we got it, was also the biggest general purpose machine on the list. And we managed to be the fourth fastest machine on the planet, which I would even consider exceptional. We were lucky with the procurement process. We got a good and powerful machine. I'll get back to that a little bit later when we see what the situation is today. But in a sense, what we have here is a machine which is compatible to what you have in your desktop. You scale up your applications, and once you go beyond what your own system is delivering, you could apply for one of the cycles on such a European machine. Of course, SuperMUC is not the first machine we had. It's just kind of, for us, the last instantiation, and we always had machines trying to follow that curve. So you have the year at the bottom line, and on the vertical line, you have the performance and the storage capabilities. And following this exponential growth, we are trying to make sure that at the front line of research, you have the computing power that you need for your daily work. That is our task. And that, of course, continues with SuperMUC phase 2. And at the moment, we are already working on the procurement of the next phase. Now, that has effects and requirements on the users. You need to make sure that you are basically following the characteristics of SuperMUC, or following the characteristics of the machine. One of them is the number of cores. I mean, this is just the last 4 machines, and the number of cores have been steadily increasing. Yeah? We're going from basically 1,500 cores to about 230,000 cores. So is your software capable of using these cores? And actually, you should use it efficiently. That's the other point. Yeah? So you need, as we've heard before already, do that efficiently. We also see these, I don't want to go into details here, but these are basically graphs pie charts which give you ideas on the number of applications and how many cores they are using. So not all of these applications are using the full machine. Actually, we have about 15 to 20 applications which can use the full machine. And the machine is built specifically for making that possible. But the point is that, of course, many cores, many applications are using smaller versions and scale up only in those cases where the data goes up. Now, we can also see a similar effect if we take a look at the top 500 list. That's the list from 1996, and it gives you basically the position of the top 500 list and the number of cores in these systems. So in 1996, most of the systems were around 100, between 10 and 100 cores, which we will remember. If we go further into the future, we see 10 years later, we are somewhere between 1,000 and 10,000 cores. And again, 10 years later, we see the situation last year where there are machines around 100,000 cores, and then, of course, there are some few machines with 1 million cores. So if we just continue that trend, 10 years from now, we will all have 1 million cores available for doing the research. And I'm just wondering what my mobile phone will have in 20 years, how many cores will be running on that. Now, I also want to give you some ideas on the applications. This is an application that was competing for the Golden Bell Award from two groups at both universities in Munich, and they were working basically on the simulation of seismic activities in a volcano. And they were able to use 147,000 cores of SuperMUC with a production speed of 1.4 petaflops. So with a peak performance of 3.2 petaflops for that system at that point in time, we were able to do 44.5% of peak performance for production runs. Now the production run here needs about 5 to 7 hours. So that means you use the entire system for 5 to 7 hours for only one application. And that is, of course, also associated with costs. I'll get to that in a second. The other point is, of course, even if it looks general purpose and very kind of homogeneous, the architecture in the background is, of course, already complex. So this is the architecture of the system, and don't take in all the details. I just want to impress you about the complexity. And I consider that a very simple system compared to what the next one is. So we are also getting up there. And if you want to use the entire system, you need to take into account things like the amount of memory per core. Peter is nodding, yeah, for those of you who don't see, because that's one of the challenges today. Yeah? We have many cores. We also need to know how much memory we have per core. If we take a closer look for the two phases between SuperMUC, that's all x86 processors. As I said, the same one as we have on your desktop. But of course, there's much more characteristics here which we need to take into account when we are programming these systems. And actually, if we take it a little bit closer, what you're applying for is access to one of the machines at one of these three centers. So there is already three different systems, and somebody decides which of the system fits best to your application requirements. So you basically are already fixed on one of the systems depending on what your application is doing. Now the other point, as I said, efficiency. Why is it important to run efficiently? This curve gives us the power consumption of the center. And you see that we have been steadily increasing. So consider that for your home. That would mean your power bill goes up and up and up, and you find all the devices your kids have been placing around the house. Yeah? In our case, of course, it means we have already, with all the systems that are getting in here, SuperMUC is coming in, we are increasing the power bill. And we are still limited by the public funding. So there is a budget envelope, and we can only spend so much power on it. And we had a discussion over drinks yesterday, and one of the points was we are now in a situation where the computing capability is basically limited by the amount of power the amount of electricity we are able to pay for. So we are coming to a point where we are buying bigger machines that we can actually run with the power pool that we have available. And if power gets cheaper, we could do more computation, which is also something to keep in the back of the mind. Now for SuperMUC, what we did, and I should mention just as a rule of thumb, the power consumption at our center is, for 1 hour, we're spending about 1,000 euro just on electricity, which also means in 3 days we are spending the annual budget for 1 PhD student just on electricity, and in 1 year we are spending 120 PhD students on electricity. Something to keep in the back of the mind. Now SuperMUC is a positive example. I believe it's one of the most energy efficient systems on the planet. The reason for that one is, for each of the cabinet, that's the empty room before SuperMUC came in, we have these water cycles, these water connectors. And SuperMUC is the first machine on that scale that was using warm water cooling. Now the question is always, why should a user be concerned with running energy efficiently? Why is this? I mean, I want my code. You want your exact scientific experiments to be done on the system, yeah? Well, actually, the reason is, if you and we together are able to save some energy, we could use it for other application. And that goes back to you. So you can compute more if you're running more energy efficient. And we're trying to do research from a computer science point, making sure that the system is running as efficiently as possible. And that needs to be taken into account when you run your system. Actually, we are trying to run your code with the optimal frequency, as one of the examples. We are trying to increase the cooling temperature. So SuperMUC is cooled with water that can be up to 36 degrees Celsius warm. And then using some of the effects that outside as today is usually colder, so we don't need any energy to cool down the system. Now, the saving, just by the measures we did for SuperMUC, is 2 million euros just in electricity for making sure that we put all these energy efficiency parameters and tools into the system. Now, that all comes back to the user, and here we have one application. That is Peter Coveney's application. Peter and his group, some of the people are here also in the room, have been using SuperMUC, and they were actually the first ones to ever use SuperMUC phase 1 and 2 together. Now, Peter's application was running on 37 hours, so I think we started Friday lunchtime and then basically used all the weekend, and then they had to finish on Monday morning to go back to regular operations. They've been using 240,000 cores, consumed 8.9 million CPU hours, and produced some 5 terabytes. All nice numbers. But that's not the important numbers here. The important thing was when we talked, I think we talked on Tuesday that week, and Peter told me, you know, it's fantastic, we got some new results. And that is the important thing. And actually Peter also gave me just, I didn't know that was just recently published. That's the magazine of the Bavarian Academy of Sciences and Humanities. And there is a huge article in here which basically shows how we got from the original small-scale experiments to something that Peter has been doing. Now, Peter's application has also one strange characteristic. It is not the kind of application that usually run on the system. So he comes in with something that is new, that is different. But what he's doing is, he's again pushing the front. He's basically putting something new in, which we need to take into account when we talk about the future. So that's what I wanted to do with you. Now, one of the things we see is we need to invest in the future. Just by taking the previous system to SuperMUC, we had an increase of a factor of 50 to 70. Just the performance increase is enormous. And while we increased the performance by a factor of 50, the power consumption was only increased by a factor of 3. So at one point, it is cheaper to get rid of the old stuff, put some new stuff in, get more performance at less price for the electricity. And that's an interesting point. Now, of course, we also need to take into consideration other things. And I mentioned the next machine, codenamed SuperMUC Next Generation at this point in time. So I'm not allowed to talk too much about the procurement, but I wanted to give you some ideas of where we're going to. One idea comes from the top 500. If you take a look at the top 500, and you were right, Pitstein is position 8, as we see on this slide, all these systems are using accelerators, or most of the systems in the front. Actually, we also see that the performance is kind of not increasing as much as it used before. We see this little breakdown, and we see that we get the performance only if we invest in different kinds of accelerators. So actually, as you see here, at least 80 systems are already using accelerators for one or the other task. And especially those systems in front have to use accelerators. So if you want to continue advancing science, we need to think about these things. Yeah? What is not only the typical application mix, like number of cores, the memory per core, the interconnect, those typical things that you think of an HPC machine, but also how many accelerators would you put in? Is there a place for virtualization? Actually, you also mentioned it, so as I said, I don't need to talk anymore. The point here is, of course, you need to adapt your workflow to a system so that the supercomputer is only one step in your workflow. And in order to do that, to give you the flexibility, there needs to be something that uses virtualization or cloud technology to make sure in your workflow, and then you go from there to the supercomputer. You have different systems, workflows, high throughput computing, and as I mentioned, we always need to go down with the power consumption. If we get the budget for the new machine, the budget for the new machine means it's iron, it's electricity, and it's some manpower, some humans. So we need to make sure that the electricity is a small part in order to have enough for the next machine itself. So I'm coming here to one last slide. This is kind of an overview. This is a conceptual slide, which is kind of giving you the idea, but not enough details about what the system will be. We will continue to have general purpose HPC nodes, simply because we have this wide variety of applications, and they can live here without changes. Those codes that want to be faster or need more performance will need to have some kind of accelerator or many-core or whatever. So we have the heterogeneity in the system itself. We will also think about one important factor is all the storage capabilities, and the other thing is that we also need to think the interconnection to the outside world, which will be done by cloud. So the cloud is a forefront. It's kind of the entry point to the big machine. And then what we didn't talk about so far, but we saw some nice pictures in Anna's talk, was all this issue about whenever we compute here, we need to analyze at one of the points. So the point here is the next systems will look more like this, heterogeneous, and you need to consider how that fits best to what your application is doing and how could you adapt your application to that. Let me just finish with 3 more slides. One of the things I'm mentioning here is it works only if we work together. And putting the role model here and some other people in the room, Marian Bubak over there is a similar example to myself. He's also working with the users. And it is very important that we see this as a partnership. We need this partnership in order to make sure that we are exploiting the machines as best as possible. We get the input from you, we understand better what you want to do, and we can make sure that the computer science aspects is being dealt with. The other point, and that is mentioned in a paper here, I'm not sure if the slides will be available, I'm happy to give them away. The other point is, of course, that we see that there is a pattern on how this works together. One of the important things here is this is our cookbook. We do this for the partnership. And basically, we always kind of do these workshops, which are incremental. So we need points where people sit together. Actually, whatever you saw in terms of applications was done in a workshop where people were sitting together at a desk for a couple of days trying to get their codes up. And the good results that I was able to demonstrate are direct conclusions from that, because sitting together, making sure that the applications work together gives the benefits. And with that one, I thank you for your attention. I'm ready if you have any questions.